All right, welcome to The Explainer. Today we're going to talk about something that's, absolutely fundamental to computer science, the linked list. So, you're probably familiar with arrays, right? They're kind of like a bookshelf. You've got all your books stored side by side, neat and tidy, in one continuous block. Linked lists, though, they're a completely different beast. Instead of a rigid shelf, picture this: a treasure hunt. It's like a chain of clues, where each clue leads you to the next one. It doesn't matter where in the world the next clue is hidden. What matters is the connection. So let's just dive right into that treasure hunt analogy. It's honestly the best way to understand this. Okay, so every treasure hunt is made up of, well, treasure chests. In our world, the basic building block is called a node, and this node is our treasure chest. Inside, you'll find two things. First, the treasure itself. That's our data. And second, a map. This map is super important. It's a pointer that tells you exactly where to find the next treasure chest. And of course, every treasure hunt has to start somewhere. You can't just wander around hoping to find a clue. That starting point, that very first map you're handed, is called the head. It's the key that kicks off the whole adventure, and it's the only piece of information you need to find everything else in the chain. Now, here's where it gets really cool. Where are these treasure chests actually buried? Well, they're not lined up in a nice, neat row. Nope, they can be scattered all over your computer's memory. One could be here, the next one way over there. The physical location doesn't matter one bit. The only thing that ties them all together is that logical chain of maps. This whole idea is sometimes called memory fragmentation, and it's what gives linked lists their flexibility. Okay, so let's use these pieces to build the simplest version of this chain. This is what we call the singly linked list. So you've got your list. How do you actually read what's inside? Well, you have to follow the clues. We call this traversal. You start at the head, right? You open that first treasure chest, you grab the data. Then you look at its map and follow it to the next chest. And you just keep doing that over and over. Chest, map, until you open a chest and find a map that just says, "The end." That's a null pointer, and it's your sign that the hunt is over. You've reached the end of the chain. Now, this whole setup has some huge advantages. Let's say you want to add a new clue, but you want to put it right at the very beginning of the treasure hunt. How hard is that? It's super easy. In fact, it's incredibly fast. All you do is create a new treasure chest, make its map point to the old starting point, and then just say, "Hey everyone, this is the new head." That's it. It's what we call a constant time or O of 1 operation. Doesn't matter if the list has 10 items or 10 million, it's always that fast. But there's always a but, isn't there? Here's the trade-off. What if you need to find, say, the 50th item in the list? Well, with an array, you could just jump right there. But with our treasure hunt, no way. You can't just magically appear at the 50th chest. You have to start at the beginning, at the head, and follow 49 different maps to get there. It's a long trek. This is an O of n operation, which is a fancy way of saying the time it takes to find something grows with the size of the list. So you see the trade-offs here, right? On one hand, you get this amazing flexibility. The list can grow as big as you need it to, and adding things to the front is lightning fast. But on the other hand, the limitations are pretty big. You can't just jump to an element. You can't go backwards. And even something as simple as finding the very last item means you have to walk the entire chain. So that begs the question: can we do better? Can we upgrade our maps to make this whole treasure hunt a little more powerful? Let's go back to that can't go backwards problem, because it's a big one. Imagine you're deep in the treasure hunt, you've just found a chest, and you realize you dropped something at the previous chest. What do? With our simple one-way maps, you're totally stuck. You'd literally have to go all the way back to the start and follow all the clues again just to find the spot you were just at. So, what's the solution? It's brilliant in its simplicity: the doubly linked list. The idea is this: each treasure chest now has two maps inside. You still have the forward-pointing map that takes you to the next chest. But now you also get a second map, a backward-pointing map that takes you to the one you just came from. And let me tell you, this backward map is an absolute game changer. Why? Because now if you're standing at any treasure chest in the middle of the chain and you want to remove it, you can do it instantly. Seriously. You just tell the chest before it to point its forward map to the chest after it, and you tell the chest after it to point its backward map to the chest before it. Boom. The node is gone, the chain is relinked, and you never had to go back to the start. It's another O1 operation, as long as you already know where the node is. But wait, there's another upgrade we can do.
What if, instead of the last treasure chest having a map that says the end, what if its map points all the way back to the very first chest? Now you've created a loop, a circle. This is a circular linked list, and it's perfect for situations where you need to just keep cycling through things over and over again, like in round-robin scheduling. There's no start or end, just a continuous loop.
Okay, so this all sounds amazing, right? This flexibility, this clever pointer magic, it seems like the perfect solution. But all of this comes with a hidden cost, and in the real world, it's a very significant cost. You see, if you look at the theory, just reading every item in a linked list should take about the same amount of time as reading every item in an array. They're both O of n, after all. But in the real world, it's not even close. A linked list can be 10, 50, even 100 times slower. And the entire reason for this huge difference comes down to one thing: the way modern computers are built, specifically something called the CPU cache. So here's the deal. Modern CPUs are all about speed, and they have this tiny, super fast bit of memory right next to them called the cache. When you ask for some data, like the first item in an array, the CPU is smart. It says, hey, they'll probably want the next few items too. So it grabs a whole chunk of that array and puts it in the cache. That's called prefetching, and it's lightning fast. But with a linked list, that whole strategy goes out the window. The next node could be anywhere. The CPU can't guess. So for every single node, it has to make a slow trip all the way out to main memory. This is called a cache mess, and it is the mortal enemy of performance. And this table, really, it just lays it all out perfectly. Just look at that top line. Access by index. For an array, O of 1, instant. For a linked list, O of n, a long, painful walk. But then, look down at insert at head or delete a node for a doubly linked list. Their roles are completely flipped. The linked list is O of 1, while the array can be slow. This is the fundamental trade-off. You're always choosing between fast random access and fast insertion/deletion.
So, we've talked about the simple chains, but you have to understand, this is just the beginning. Computer scientists have taken this basic idea of nodes and pointers and have built some truly wild and powerful things on top of it.
Just as one quick example, picture our treasure hunt again. But now, what if some of the maps were special? What if some maps let you skip the next 10 clues and jump way ahead? That's kind of the idea behind a skip list. It's a linked list with extra layers of pointers, like express lanes on a highway. It lets you zip across the list, making searches almost as fast as an assorted array, but you still get that awesome flexibility for adding and removing items. It's pretty incredible. Which really brings us back to the central question, the one every single developer has to ask themselves. We live in a world that is obsessed with speed, right? We're all about squeezing every last drop of performance out of our hardware, all about cache efficiency. So in a world like that, when is it worth it? When is the beautiful, dynamic, elegant flexibility of a linked list actually worth paying that very, very steep performance penalty? And the answer, well, it always depends on the specific treasure hunt that you're designing.